Hello, everybody. This is going to be my third attempt to make a video for this lesson, so I'm really hoping that it works this time. All right, so first off, you're going to want to open up the lesson 19 slides. You're going to want to open up the assignment that goes with it, and you'll want to open up the periodic table. I've also opened up this other table right here because I'm going to highlight where metalloids are again, but that'll come in a little bit. All right, so lesson 19 at the beginning. The octet rule, very simple idea. The octet rule says that all of my elements are going to want to have 8 valence electrons. That's why you have octet here. See, what's happening is elements are looking to bond with other elements and get as stable as possible. And getting stable involves gaining or losing electrons. And the whole goal is to gain or lose or sometimes share electrons until the atom only has 8 valence electrons. Valence electrons, if you've forgotten, are the electrons on the outside shell of the atom. So it starts off with the inner shell that only holds 2, and then it gets to a whole bunch of shells. The next one holds 8, and it keeps on going out. The most you can ever have on the outside is 8, and that's as stable as an element will be. So it always wants to manipulate things to have 8 valence electrons on the outside shell. Now remember, in order to figure out how many valence electrons something has, this is where if you have your periodic table, I suggest you print one. Print this off right here, this exact file. Print this and then start drawing on it. Up here, you should write 1 VE to remind yourself that everything in the first column has 1 valence electron. And then at 2, you have 2 valence electrons. Skip your transition metals, and right here you'll have 3, and then 4, 5, 6, 7, 8 valence electrons, okay? So this is how you determine how many valence electrons you'll have. You see what column it's in and look up top to decide how many any given element will have. So the only exceptions to this, everything wants to get to 8 valence electrons except for the first 4 elements, hydrogen, lithium, beryllium, and then of course helium. They're happy with only 2 valence electrons rather than 8. This is because, as I said, that innermost shell is small. Imagine if you have rings going all the way to the outside. The inner ring is going to be really small. And so since these all have 4 or less total electrons, they'd rather just get to 2, so their outer shell, which is their only shell, is full with 2. But everything else wants to get to 8. They want to fill it up. So look at this first question. Why is beryllium an exception? The question is, why is it an exception? So instead of 8, what would it rather have? It'd rather have 2. All right, now you're going to decide if these elements are going to gain or lose electrons. And here's what you're going to do. They want to rearrange the smallest number of electrons possible. So if I'm in a classroom, for example, and I'm told to only have full classrooms, so either fill up the room or empty it, but move as few students as possible. If this room fits 20 students and I currently have 19, what's easier? Get all 19 out of there or put one more in and have a full room? We'll just put one more in and have a full room. If I have a room of 1 or 2 students, what's easier? Add 18, 19 students and fill up that room, or just get the 1 or 2 in there to leave? Well, get the 1 or 2 in there to leave. Same idea when we're doing the octet rule. If a shell out here has 1 or 2 electrons, if I can just get rid of those, the next shell in was going to be full, okay? If I'm out here in this shell and I have 7 electrons, what's easier? Get rid of those 7, go to the next shell, or just add 1 more and fill up the shell I'm at. Well, if it's at 7, just add 1 more and you're at 8. So basically, if I have less than 4 valences, it's easier to lose the valences I have. If I have more than 4 valences, it's easier to gain and get to 8. So what I'm going to do for each of these questions is I'm going to look at the periodic table and we're going to think. I'm going to do the first one, and then I'm going to have you run through the next few. In order to be stable, would chlorine gain or lose electrons? Let's find chlorine. It is right here. Look up top. You see 7. Chlorine has 7 valence electrons. What would be easier, to lose all 7 and get back down to the previous shell, or to gain 1 and fill it up? The answer is gain 1. So chlorine wants to gain valence electrons. I want you to try calcium, oxygen, hydrogen, and iodine. So press pause, try these, and then I'll run through the answers. Okay, oxygen is going to gain. Hydrogen's kind of weird. It's at 1. Remember, it wants to get to 2. It's an exception. So it just gains 1 to get to 2. Iodine is going to gain. Hold on, did I skip? Oh, I skipped calcium. Calcium wants to lose. It only has 2, so it's easy to lose 2. So calcium has 2 valences. wants to lose and get 0. Oxygen has 6, it wants to gain 2. Hydrogen has 1, it wants to get to 2, it's an exception, so it gains 1. Iodine, that's at 7, it wants to gain 1. What type of bond would you expect to form? So let's look at bonding types. There's 3 types of bonds. The way bonds work is we look at the electron affinity. If 2 elements have a high electron affinity, neither one wants to give up the electrons, so they're going to share electrons. Remember, electron affinity increases as you go up and to the right. So this upper right corner right here has the high electron affinity. If you have not already, I would suggest you take the periodic table, you print off this document right here, this black and white document, and you start drawing on it. So I told you to write the 1 through 8 up along the top. I also suggest you shade in where the metalloids are. We went over this on a previous lesson, and hopefully you shaded in your periodic table. What you have B, Si, Ge, As, Sb, Te, and At are your metalloids. So basically you make a step right here, but you skip the Po and the Al. So these are your metalloids. To the upper right of those are your nonmetals. And these are the high electron affinity that fight over electrons. So if 2 nonmetals bond together, they fight over the electrons, so they share it because they both want it, and you get what's called a covalent bond. The next type of bond is if you have different electron affinities. So if I have something way over here that gets rid of electrons, something way over here on the left, and something way over here on the right that gains electrons, one is going to give, one is going to take. And this would basically be if you have a nonmetal bonding with a metal. When a nonmetal bonds with a metal, one gives, one takes. Giving and taking will form cation and anion. So since you're making 2 ions, it's called an ionic bond. So that's between a metal and a nonmetal. And lastly, if 2 metals bond, it's a metallic bond. So let's look at the questions. Between chlorine and fluorine, let's look at where they're at on the periodic table. Chlorine and fluorine, both up here in the upper right. If I even pull up this version of it, chlorine and fluorine up here in the nonmetals. What is it when 2 nonmetals bond? That is a covalent bond. Okay, I want you to try do 8, 9, 10, and 11, and then I'll run through it with you. So press pause and go all the way to 11. Okay, Cl and Mg, that's going to be a nonmetal and a metal, so that's ionic. Cu and Zn, that's 2 metals, so it's metallic. O and S, 2 nonmetals, covalent. Be and Br, metal, nonmetal, ionic. What is the trend for increasing electronegativity? This is something you need to remember from a previous lesson. Remember, down and to the left was atomic radii, and the electronegativity was up and to the right. So the trend, it increases as you go up and to the right. All right, so here's why I have the camera running right now. I'm going to draw a few things on here. This is not extremely important for today, but it's necessary to understand where we go from here in the next lessons. So covalent and ionic bonds are affected by something called polarity. Polarity, if you think about on our planet, we have the North and South Pole. Or you think about if you say these 2 people are polar opposites, or this is a polarized issue. That means that people seem to have 2 very different opinions. Polarity is what happens if you have different sides when a bond happens. So a bond is polar if the electrons are unequally shared between atoms. So it helps to draw the orbital notation when we do this. So let's do diatomic hydrogen, okay? Remember orbital notation. Actually, before I do that, let's do hydrogen. Hydrogen has how many valence electrons? Only 1, okay? And remember, hydrogen wants to get to 2. If it gets to 2, it's happy. So let's think if you have hydrogen right here, and remember the orbital notation. You do 1, 2, 3. It's 1, 2, and then 3, 4, 5, 6, 7, 8. Remember the dot notation we did. Hydrogen is just going to have 1. And if you have diatomic, that means you have 2 of an element. If I have diatomic hydrogen, that means I have 2 hydrogens. So this has 1 electron, that has 1 electron. So what's going to happen with this, I'm going to rearrange it so the electrons are in between them. So here's the electron that came from that hydrogen. Here's the electron that came from that hydrogen. So here's this guy's electron. Here's that guy's electron. Okay? Well, the electron is going to be, who's going to win a fight? Hydrogen versus hydrogen. Well, it's going to be a tie. So if they're fighting over these electrons that they both want, they end up right in the middle of them. So what happens, this zone has electrons. Are electrons positive or negative? Negative. So the middle is going to have a negative charge. The side over here is going to have a positive charge because hydrogen has a nucleus with protons, and the side over here has a positive charge. Are your two sides any different? No, both sides are positive. So what happens if you have hydrogens fighting over electrons, it's going to be called nonpolar. The reason it's nonpolar are there two different poles. Is there a north and south pole? Or like a polar, right now, there's, I don't know, maybe I use this video again in a few years, but at the shooting of this video, there's an election going on. Very polar. People are either lean right, they lean left. They're Democrat, they're Republican. Is it Democrat, Republican here? Is it left and right here? No, it's two positive sides. Both are exactly the same. So it's non-polar. I did not mean to go to that view. So then let's consider hydrogen and fluorine. Now let's look. Hydrogen's way over here with 1. Fluorine is all the way over here, but look at which one is further to the right? That's fluorine by a lot. So when they fight over electrons, fluorine is actually going to win. So here's what's going to happen. If I have hydrogen and fluorine, here's hydrogen. Here we go. So here's hydrogen, and it has 1 electron. And here's fluorine. It has 7 valence electrons. So remember the electron configuration. You go 1, 2, 3, 4, 5, 6, and 7. Okay. Now let's rearrange it. The one single element, let's face it towards the hydrogen. So let's just rearrange the drawing. So hydrogen has this electron, and then fluorine has all of these electrons. Remember, I'm going to draw that one loner electron. I'm going to have it face the hydrogen, and it's going to be like this. So see, by doing that, fluorine now has 1, 2, 3, 4, 5, 6, 7, 8 like it wanted. Hydrogen has 1, 2 like it wanted. So it's a good arrangement. If they stand next to each other, rearrange the electrons so like they can both share, it'd be like if this is the valence shell for fluorine, this is the valence shell for hydrogen. They're both happy. You see how that's going to work? Here's the problem though. Fluorine is much stronger than hydrogen. So it's really going to do something like this, where fluorine, even though this was hydrogen's electron, fluorine is way stronger, so it's going to hog it. It's kind of like whenever I share a cup of coffee with my wife. It'll be always next to her, and I'll get 1 sip for every 10 sips she gets. So we don't share coffee. We each get our own. So fluorine is hogging all the coffee. So what's going to happen if you look at this under a microscope and you have some type of way of viewing positive, negative ends, all the electrons are over here. So that's a negative end. Over here is a positive end. So you have a negative and a positive end because all the electrons go over here. So that's polar, meaning one side is different than the other. Now what's going to happen, the fluorine end of the molecule and the hydrogen end, they're going to be, you have a positive end at the hydrogen, negative at the fluorine. So what happens, I want to ask you a question. I want you to think out loud. What's going to happen here? What's going to have a stronger bond? If I have this situation where hydrogen just nicely shares it right in the middle, and it's a positive and a positive end, or if I have this situation where fluorine hogs all the electrons, so I have a positive end and a negative end. Which one of those bonds is stronger? This one right here, where I have a positive and negative end, because opposites do what? They attract. So if I'm able to make it so both ends, where there's a positive and negative, there's a strong attraction. And so the more polar the bond gets, meaning the bigger difference you have when they're fighting for electrons, if the tug of war makes it so all the electrons go to one side, you get a much stronger bond. So what I'm about to ask you is to look at the strengths of bonds based on the elements. And what you're going to think about is the electronegativity, their ability to attract electrons. If it's way different between them, you'll have a really strong bond. So what was the trend for electronegativity? It's stronger when you go up and to the right. By the time you see this, I don't know how this gets all flipped, so up and to the right. But on the periodic table, this upper right corner is the strongest. So up and to the right is going to have higher electronegativity. And in order to have a strong bond, you need to have a big difference in electronegativity, meaning have weak electronegativity on one atom and strong electronegativity in the other atom, that'll allow you to have a positive and negative side. So when we do these, let's look at something like fluorine and rubidium. Look on the periodic table. Fluorine, all the way up here in the upper right corner. It has the highest electronegativity. And then let's do rubidium, all the way over here down in the bottom towards the left. Super low electronegativity. These are going to make an extremely strong bond because it'll be very negative on the fluorine end, very positive on the RB end, and that's going to be a very, very polar bond. Whereas fluorine and oxygen, sure, it'll be polar because fluorine is a little bit to the right. It's going to win, but it's not going to be very polar because they both fight for electrons, and it's not going to be like way negative over here and way positive over here. So basically the trick right now, upper right is strong, bottom left is weak. The greater the difference in their electronegativities, the stronger the bond will be. Look at this right here. Here's the point. The greater the difference in the electronegativities, the stronger the bond will be. Remember, electronegativity. Upper right is strong, bottom left is weak. So this is the last concept you need to be able to do. I'll cover this slide after we look at these examples. So which has the stronger bond, Ba with Cl or Ba with I? So think about which one of these is further from Ba is basically what you're thinking about. So Ba, barium, is way down here, bottom left. Bottom left. So what's going to be stronger? Barium when it bonds to I, which is right here, pretty far away, or chlorine all the way up here in the upper right. Which one is going to have a greater difference from the Ba? That would be the chlorine. So which has a stronger bond? Barium and chlorine. All right. I want you to try the next two. Make sure you get it, and then we'll move on. So press pause, try these two, and then we'll look at that last slide. All right. So here we go. Chlorine and chlorine, chlorine and fluorine. Do you even need to look at the periodic table? You shouldn't. Is chlorine and chlorine, is either side going to win? No, it's a tie. So both sides get to be positive. So what you have here is no polarity. Whereas with this, one of them is going to win. And if you look at it, you'll see the F wins. It's higher up, but you don't even need to look it up. Obviously, there's going to be a difference here, a positive, negative side. Right here, it's a tie. So your stronger bond will be Cl and F. And then lastly, I and SR or I and F. So let's pull up periodic table. Here's I. So we're asking I with SR or I with F. Well, let me see. Let me make sure I'm doing that right. You know what? This is a typo. I'm going to change this. This should be saying SR with I or SR with F. Okay, I'm going to change it. This, by the time you look at this, it's going to say SR and I or SR and F. And in that case, the correct answer is going to be SR and F. Okay, so I'm going to switch that when you see this. Right now, it's a typo. Why is it impossible to have an entirely ionic bond? Okay, here's what we have. Remember, ionic is when one of them totally gives it to the other, positive and negative side. Covalent is when they share. So here's how it works. You can have 100% covalent bond, perfect sharing, if it's two of the same element, two of the same nonmetal. Then they're going to share between them. But you can never have a perfectly ionic bond. An ionic bond means that you've completely given one electron to the other. That will never happen because even when one gives it away, like in the case of hydrogen giving it to fluorine, hydrogen is still slightly attracted to that electron, so it's still going to kind of hold it. It would kind of be like if I give you something, but every couple weeks I still ask to use it. Is it like I totally gave it to you then? Not really. It's kind of like we're sharing it, but I let you have it most of the time, right? And that's the best elements can do. They can have a arrangement where it's like they're sharing, but they're letting the other use it most of the time. So that's why you can never be fully ionic, because even the one donating the electron is still going to be somewhat attracted to it. And that's the answer to your last question there. All right. So this one will be edited, and hopefully this video works this time. If you have any issues, please just email me and we'll get it sorted out.